Our next one involves things that we talked about this morning in lecture. Let's see what's going on here. So if you notice, first thing that I see, I get to looking over here, here's a diene. Got a phenyl halide, we got a diene, but here I see a strong base, a very strong base. So that very strong base, we'll want to make a benzyne out of our phenyl halide. So that strong base goes through and makes the benzyne. I'm not going to go through all that mechanism. Make the benzyne, grab the beta hydrogen electrons, left on the carbon, then they kick in, form the triple bond, and kick the bromine off, so you get the benzyne. Now, benzyne is going to act as a dienophile, and it will react with our diene. So this is our our Diels-Alder reaction, sorry. You make a 6-member ring with the new double bond. We still have the phenyl group over here on the other side. And there's your product. If you want the top view, that's the side view. If you want the top view, here's looking down from the top. You can draw it either way. That would be fine. It does not have an enantiomer because there's a plane of symmetry through there, so there is no enantiomer. We always have to watch that with Diels-Alder, but there is no enantiomer present.
Why wouldn't we have to do a dash? Why wouldn't we have to do dashes on the other part of the ring, like the other benzene ring?
Here? Because that's a double bond. Double bonds are flat.
All right. Yeah.
Phenyl ring's flat.
Okay.
There is no dashes or wedges. That's flat. That's sp2 carbons. All sp2 carbons are flat.
Okay.
Other questions? Okay, our next one. First step, I have BF3 and some heat. BF3 is a Lewis acid. That is going to be our Lewis acid catalyst. Now, we talked about when we covered this that alcohols, for some reason, love BF3. We usually use other catalysts for the alkyl halide. I mean, for alkyl halides or any of those others, but you can use any Lewis acid catalyst. But if we're going to do an alcohol, we normally always do BF3. They just work really well with an alcohol. So the alcohol gives a pair of electrons to the boron, and that puts a plus charge on the oxygen, and that leaves. So I'm going to skip ahead if you don't mind. And that gives us a carbocation. So it pulls that off and makes a carbocation. Now, anytime we form a carbocation, we need to watch for a rearrangement. That is a secondary carbocation that will rearrange. We will do a hydride shift. We're going to do a hydride shift to get a tertiary carbocation. rearranged from a secondary to a tertiary. Now we're going to take the carbocation and react with our aromatic ring. Now we got to decide where are we going to put that alkyl group. That alkyl group's going to go onto the ring, but you have to decide where it's going to go. The groups that are already on there will do the directing. Now we've got to decide which one wins out. I got two groups on there. Here we have a carbonyl. Carbonyl is partial positive charge. That is a meta director. That is a moderately deactivating group. Moderately deactivating group. On the other side is a phosphorus. Uh-oh, that was not on our list that I gave you of all of these activating and deactivating groups. What do I do?
It has lone pairs.
It's got lone pairs, so we know it's an ortho pair director. It's an ortho pair director already, it's going to win out. You don't even have to think about it. It's going to win out. On the periodic table, phosphorus is right below the nitrogen, so it's going to act probably pretty similar to the nitrogen. So if that had been an NH2, NH2 is a strongly activating group. Phosphorus might be strongly activating, probably more likely, since it's a bigger atom, it's probably going to be more moderately activating. But anyway, it's either moderately or strongly activating. Any activating group is going to beat a deactivating group. This is some type of activating group. I'll just say activating. It's either going to be moderately or strongly activated. It's an ortho pair director because it's got a lone pair of electrons. So that one wins. Any activating group always beats a deactivating group. So this wins. It's the phosphorus that's going to tell our electrophile where to go. So this is ortho to the phosphorus. There's meta, there's para. There's already something in the para position. So we're going to go to one of those ortho positions. I'm not going to go through the mechanism there, just a standard electrophilic aromatic substitution. There's our product. Now it turns out you really couldn't screw this one up, because even if you went with the wrong group, it's the phosphorus that wins, but even if you went with the carbonyl, that's a meta director, and it would have sent the alkyl group to the same spot. This is meta to the carbonyl, so that one was kind of foolproof. But technically it's the phosphorus that wins out there. Questions? So the tricky part of that one, you had to watch for cation rearrangement. On Monday, if you get through with your exam and you did not do a cation rearrangement somewhere, I'll go back and double check. More than likely, I'm going to have a cation rearrangement on there. I tell you to watch for it, you better watch for it. Okay, let's take a look at this one. First step, we have sodium hydride. Sodium hydride is a strong base. And hydride, full negative charge on the hydride. So what's it going to do? Any thoughts?
It's gonna hook something to protonate.
Not protonate, it's going to pull the proton off.
Yeah, from the
Acid's protonate.
Yeah.
Bases pull protons off. So this is going to pull off the proton off of the OH. That's a very acidic proton. pKa of about 10. That's a phenol. Phenols have pK of about 10. Got a good strong base, got an acid, doing an acid-base reaction. Okay, so we pulled the proton off of the alcohol. That leaves us with an alkoxide anion. Now what are we going to do? See some nitro groups there on the ring. They're both, the two nitro groups are ortho to that tosylate. Now what did we learn about tosylates? Back in chapter 11. Tosylate, mesylate, and triflate. Remember that?
Sure.
What do we know about those? Nope. That's TBS. TBS is protecting group. Tosylate, mesylate, and triflate. Why did we put a tosyl group on, or a mesyl group, or a trifle group? We always put them onto an oxygen. So here it's already on. So at some point somebody put a tosyl group onto the oxygen. Why did we do that last semester? Nobody remember? Somebody's bound to remember. Come on.
Makes a leading group.
Makes it a good leaving group. Yes, thank you very much. It makes it a good leaving group. So I have a good leaving group there. We have two nitro groups that are ortho to a very good leaving group. We said that with a tosylate, mesylate, or triflate, they are just as good as an iodide. So if you wanted to pretend that that's an iodide, that's fine. If you want to pretend that's an iodide, it's just as good as the iodide, if not better. Now, if it was an iodide, you know exactly what to do. I got nitro groups that are ortho to a very good leaving group. That's ortho, both of them. So what kind of reaction are we going to do here?
SN2.
A what?
SN2. That's probably wrong. I mean,
SN2 on a phenyl group?
yeah, that's a really dumb thing. SNAR.
SNAR, thank you. This is a SNAR. You need nitro groups, ortho or para, to a good leaving group to do SNAR. And I have two nitro groups that are ortho to a good leaving group. This is just a different leaving group than I did in my examples in lecture. But we have seen this one in the past. It's an extremely good leaving group. So let me go through this. Our nucleophile is going to add to that carbon that has our good leaving group. We kick the electrons into the ring. Those electrons will then kick back in to reform our aromatic ring. And we're going to kick the leaving group off. Okay, so there's our product. We did an SNAr reaction there. Questions? Okay, our next one, we have bromine and a Lewis acid catalyst. Okay, we know what that does. Bromine with a Lewis acid catalyst. This is going to react together and give us a bromine cation that's going to serve as our electrophile. And we have done electrophilic aromatic substitution. We've been reacting that with a benzene ring. What? I don't have a benzene ring. What in the world is this? What's going on here?
Use the double bonds.
Why?
Ox.
So when we've done bromine with the Lewis acid catalyst, we said that was an electrophilic aromatic substitution. We make a bromine cation. Bromine cation is going to do electrophilic aromatic substitution. Now in all my examples in class, I did benzene as my aromatic ring.
That's still an aromatic ring, not benzene.
That top part is still an aromatic ring. It's just a different aromatic ring than the benzene. This is an aromatic ring. That's what I was trying to get to. Bottom part's a non-aromatic, but that top ring is an aromatic ring. I can do electrophilic aromatic substitution on any aromatic ring. So our bromine cation is going to add to that ring. Now, we only got one position to go to because we have to substitute a hydrogen. So one of these two does not matter. It's symmetrical. You have to go where there's a hydrogen because this is electrophilic aromatic substitution. You substitute a hydrogen on the ring with the bromine. So there's our product. It's the same mechanism as what we've done with the benzene ring. There's no difference in the mechanism. So we're going to take the double bond out, grab the cation. We want to get our aromatic ring back. I also need to get the Lewis acid catalyst back. So we're going to take the bromine off of this to come and grab the hydrogen. That will make HBr. We get HBr as a byproduct. I also get that gets me my Lewis acid catalyst back. And then that gives us our aromatic ring back as well. So this was just electrophilic aromatic substitution on a different aromatic ring than we were used to looking at. All of my examples in lecture was benzene rings, but any aromatic ring will work. Doesn't have to be a benzene.
Why did we put the BR at the top of the bottom? Can you not do anything that...
You have to substitute a hydrogen. These are the only two positions that's got hydrogen. See, these have got carbons. I can't go here because
it's double bonded. Yes.
you've already, yeah, there's already something there.
Alright.
So we're substituting that hydrogen. See, I have to pull that hydrogen off. That makes HBr as a byproduct. You can't put the bromine here because then there's not a hydrogen to pull off.
Okay. Thank you.
So you can't get your aromatic ring back. Other questions? Okay, our next one here we have hydrazine and KOH. This is the Wolf-Kishner reduction. This will reduce aldehydes and ketones down to an alkyl group. Now, while I've got this up here, next Monday we have lab midterm. And every year I get students that get confused with this. We used hydrazine in one of our labs that was with luminol. That was a different reaction because I didn't have the base with it. This is hydrazine with the hydroxide, with potassium hydroxide base. In the lab that we did, we added hydrazine straight in. We didn't have the base. We added the base later in a separate step. Added it separately there. So that's a different reaction that we did in the lab to do the luminol. So this is a Wolf-Kishner reduction. This will reduce aldehydes and ketones. Will not reduce any of the other carbonyls. Gets aldehydes and ketones only. So I have an ester here. I have an aldehyde. We're only going to do the aldehyde. It will reduce that down to an alkyl group. That now will become a CH3. It had one hydrogen on it, we're going to pick up two more, becomes a CH3 group. There becomes a methyl group. Still keep the same number of carbons, we're not changing that. We don't touch the ester. So there's our product with the Wolf-Kishner. Could have done the exact same thing with Clemenson reduction. I've done the Clemenson, we've got the same product. So Clemenson, either one, they're interchangeable. Questions?
Is our lab midterm on the 8th or the 1st? Is it the same day as the organic exam or is it the week after?
Oh, I said next week. I meant the next one, the 8th.
Okay.
This coming, when I say next, I meant this coming Monday is our lecture exam. The next one, I said next. Okay.
Yeah, I thought that it might be on the same day.
No, it's on the 8th. Yeah.
Okay.
The lab midterm is on the 8th. Our lecture number 2 exam is on the 1st, March the 1st. But I wanted to just point that out. This is not the same as we did in the lab. So every year on the lab midterm, people want to start trying to do a Wolf-Kishner reduction. When I do have something similar to the luminol. Okay, question 5. Is simply asking which of the following molecules tell whether they are aromatic, anti-aromatic, or non-aromatic. So let's take a look at the first one here. We have lone pairs on the nitrogen. So let's go through our rules. First rule, must be cyclic. Yep, we have a ring. Got some other stuff hanging off, but we do have the ring. Must be planar, we never know about that. Must have 4 n plus 2 pi electrons, that's the Huckel rule. Now, let's see. I've got 2 pi in this double bond. I got 2 pi in this double bond. This nitrogen is going to change its hybridization from sp3 to sp2, and that lone pair will go into a p orbital. So those are going to be pi electrons. So we've got 2 more pi electrons. These down here do not count because those are in an sp2 orbital. They are not in a p orbital. They are not pi electrons. So I gave you my little rule for that to simplify things. If the heteroatom is involved in a double bond, you don't count any lone pairs on that heteroatom. So this one is involved in a double bond. We do not count lone pairs. If the heteroatom is involved in all single bonds, which this one is, you will count 1 lone pair. Now this one only has 1 lone pair, but if we had an oxygen, oxygen would have 2 lone pairs, but you only count 1 of them. Okay, so I've got 6 pi electrons that are counting there. 6 pi electrons does fit the Huckel rule. You need 2, 6, 10, 14, 18, so on and so forth. So rule 3 is met. Rule 4 must have p orbitals on every atom in the ring, and we do. We have the p orbital there that's taking up the lone pair. We have p orbitals, of course, for the double bonds. So we do have p orbitals on all the atoms in the ring. This one is an aromatic compound. That ring is aromatic. Questions?
Do you mind explaining the rule you just said, the heteroatom?
The which?
You said the heteroatom. If it's
Okay.
involved in double.
If the heteroatom, that would be your heteroatoms are nitrogen, oxygen, phosphorus, and sulfur. That's your heteroatoms. We got 4 heteroatoms. So if you have a heteroatom in the ring, if it's involved in a double bond, you do not count the lone pair on that heteroatom. If the heteroatom is involved in all single bonds, then you count 1 lone pair.
Okay.
Only count 1 lone pair. Now nitrogen only had 1, but like an oxygen would have 2 lone pairs, but you only count 1 of them because they can't both be in a p orbital. Only 1 lone pair can be in a p orbital.
So say if that nitrogen was in a single bond, will we count both lone pairs?
So if I were to have something like this, let's say an oxygen. Now there, the oxygen's all in single bonds. So 1 lone pair is going to count, 1 will not.
Right.
So I'll have 1 lone pair that counts. I have 2 pi here, 2 pi here, 2 pi here. This would be aromatic.
Right.
This lone pair does not count. That's in a hybridized orbital. You have to be in a p orbital to count. These are in a p orbital. They can't both be in a p orbital. One's in a p orbital, one's in a hybridized orbital. So if your heteroatom is involved in all single bonds, like we are here, count 1 lone pair. Down here, that nitrogen is involved in all single bonds. Count 1 lone pair. If the heteroatom is involved in double bonds, don't count any lone pairs on that heteroatom. This does not count because it's involved in a double bond. If I had, say, this one, that lone pair does not count because the oxygen is involved in a double bond. We do not count that lone pair. So this one here would have 2 pi here, 2 pi here, and the anion would count. That's 2 pi. That's 6 pi electrons. Oop, I forgot a plus charge. There should have been a charge on that oxygen. That one is aromatic. So that's the same thing as this. It's just a resonance structure. Any other questions? Looking at my next one. Rule 1 must be cyclic. Yep, it is. Rule 2 must be planar. You never know about that. Rule 3 must have 4m plus 2 pi electrons. That's the Huckel rule. let's see what we've got. We got 2 pi in the double bond, 2 pi in this double bond, 2 in this double bond, 2 for the anion, 8 pi electrons. That does not fit the Huckel rule. Rule 3 is not met. Rule 4 must have p orbitals in every atom of the ring. We do. The anion, that's going to be a p orbital, and you got p orbitals for all the double bonds. This is considered to be anti-aromatic. Rule 1 and 4 is met. That makes it anti-aromatic. Questions? Must be cyclic. It is. Must be planar. Don't know. 4n plus 2 pi electrons. We are met here. I've got 2 pi here, 2 pi here, 2 pi here, 6 pi electrons. P orbital on every atom of the ring. Yep. On that ring, there is a p orbital on every atom. That ring, that's just a benzene ring. That ring is aromatic. The other ring is actually non-aromatic. But I don't really care about the other ring because that one is aromatic and that's all we care about. This will react just like any aromatic compound. This ring happens to be non-aromatic. You can label that if you want to, I don't care. What's important is that ring here is aromatic. We've got that benzene ring there. This one's non-aromatic. We don't have p orbitals on these atoms. There is no p orbital. So that part's non-aromatic. Questions? Okay, let's look at the last one here. We're going to do some retrosynthesis. Go backwards on some of these. So the question says, starting with toluene, it's giving you the starting material. It says start with toluene and design a synthesis for this molecule. Okay, so it says we have to start with toluene. See what we can do here. Let's see what we've got. We've got carboxylic acid group. We've got all of this that's been added on. We know how to get the carboxylic acid group from that methyl. That's a benzylic carbon. We can oxidize any benzylic carbon to a carboxylic acid using hot potassium permanganate. Always acidify in separate steps there. The first step is got a strong base. If you just write hot potassium permanganate, I'm fine with that. But technically, you always acidify in a separate step. But if you just write hot potassium permanganate, that's good enough for me. I'm not picky. I'm happy that you got that much. So most times nobody gets these retrosynthesis. Now we've got to that part. This will now become a carboxylic acid group. Maybe we should just write that down. Let's see. So that first step would convert this to a carboxylic acid. So that's got us some progress. Now I need to put all of this on. Let's see. How in the world do I put that on? Well, how about a Frito-Crafts alkylation? Gonna do that, do an alkyl halide with the Lewis acid catalyst. Will that work? So my Lewis acid catalyst would pull off the bromine. The catalyst is going to pull off the bromine and give a cation. That would give a carbocation. And then the carbocation would add to the aromatic ring, right?
Wouldn't it be meta?
The position would be
Hmm?
Oh wait, no, it's supposed to be meta.
It's supposed to be meta.
I thought it was para. I couldn't see it.
Here's our,
Yeah.
already got the carboxylic acid, so this is ortho to that. Here's meta. There's para. So that puts us in the right position. What's wrong with what I drew? A what? Hydride shift. That would do a cation rearrangement. We would have cation rearrangement here. So that's not going to work what I had up there. That would undergo cation rearrangement. Because that's a primary carbocation. It's going to quickly do a hydride shift to get us to a secondary carbocation. Plus it would be a benzoic cation. So that's going to shift very quickly. So that one would not work. Now what did we learn how to avoid any rearrangement was to, instead of doing Frito-Crafts alkylation, is to do Frito-Crafts acylation. And those don't rearrange. So we've got to do a Frito-Crafts acylation if we're going to put this on. So what we're going to need to do is we'll use an acyl chloride and a Lewis acid catalyst. And then that will put an acyl group on because the acyl cations do not rearrange. Okay, so we've made progress. Got the right number of carbons on. It's just that I have a carbonyl and I don't want a carbonyl. We saw in our product we got a CH2 right there. So what do I need to do now? We need to do a reduction of that. We can either do Wolf-Kishner or Clemenson. Either one would be fine. So Wolf-Kishner or the Clemenson. Either one will be fine. That gets us to that product. So that's our set of reagents. We do the hot potassium permanganate, acidify, and then an acyl chloride with a Lewis acid catalyst. That's Frito-Crafts acylation. And then either Wolf-Kishner or Clemenson. The Clemenson would be the best, but you could do Wolf-Kishner as well. And you can just write Wolf-Kishner or Clemenson. Or you can write out the reagents, I don't care. Either way is fine. Okay, questions? Like I said, the Clemenson would be best. So that's zinc and mercury, zinc-mercury alloy with HCl. That would be the best since we have the carboxylic acid on there. The Wolf-Kishner is under basic conditions, and so then you got problems with the carboxylic acid. But I wouldn't care either way. You can write either way, would be fine with me. So you just kind of have to work through it, look at what you got, you know, take one group at a time, and then make certain your order is correct. Once you get everything down, make certain the order is going to give you that product. We talked about looking at the order of the reagents. We had a whole section on that. Okay, our last one here. So again, it said to start with toluene. Make this product starting with toluene. So let's see what we can do. We know how to put a bromine on. Bromine is, we're going to use a bromine molecule and a Lewis acid catalyst. That will put a bromine on. Now, we've got the methyl already on there. The methyl is going to tell the bromine where to go. The methyl group is an ortho-pair director. It's going to tell the bromine to go ortho or pair. So if we were to do that, I'll just write over here to the side. If I do that, we would get the bromine in the ortho, and you'd also get pair. There's nothing we can do about the mixture, but you can separate those. So that's got a bromine on and got the bromine in the right place. Now let's put the nitro on. To put a nitro group on, it's nitric acid and sulfuric. By the way, if you forget reagents, if you don't remember what they are, you can usually look back on the exam and there'll be one kind of like that somewhere on the exam. So it's like, okay, I'm putting a nitro group on. Where was that? So back here on 4E, there was the reagents for the nitro, sulfuric and nitric acid. And probably on there again somewhere, I don't remember. Nope, that's the only one I see. But usually you can find them on there somewhere. If you've forgotten the reagents, they're usually on there somewhere. Okay, so that puts the nitro group on. So let's see if that works. To do step 2, does that put it in the right position? Okay, so one of the groups already on there is going to direct the nitro as to where to go. The methyl group is an ortho-pair director. Bromo is also an ortho-pair director. That didn't help us, but let's look at what's important is the activating abilities. A methyl group is weakly activating. That was one of our weakly activating groups. A bromo group is weakly deactivating. Activating always beats deactivating. You want the more activating group, always wins. This is the group that wins. So the methyl group is going to say go ortho and para to me. So we'll put the nitro group on. Here is ortho to the methyl and here is para to the methyl. You will get a mixture, but we will get some down there in the para position. So that will give that some of that product. Now, this one, it did not matter for this particular one. Many questions it will matter, but this one it didn't matter. We'd still get the same product if I switch my order. Some of these, the order is important. This one, it wasn't. If I had done the nitration as the first step, I'll just show you, and then the bromination, we would still get the same product. So let me just show you real quick. If I had done the nitration as the first step, so this is an ortho-pair director, tells the nitro group to go ortho and para. So we will get some para. You also get ortho, can't help that. We can separate those, so I do have the para, that's the correct position. And then you put the bromo on. You have to decide where to go. The more activating group wins. Methyl is weakly activating, nitro is strongly deactivating. Activating group wins, the methyl wins. Methyl says go ortho or para to me. So it will tell the bromo to go the ortho positions. So that way also works. Does not matter, oop, I left the 3 off right there. Did not matter the order on that one. Most of these it will matter. Just so happens this one here it didn't matter. Questions on that?